Hello everyone, welcome to this session on a problem related to strain energy method. So previous session we had solved a problem related to a strain energy method wherein it was a cantilever beam subjected to a point load at the free end, and we were supposed to find out deflection at the free end of the cantilever beam. Now same example, that's same continuation, same procedure we are going to adopt for a other statement which has been mentioned here, which is for the simply supported beam. The statement of the problem goes like this: it's a simply supported beam of span L and which carries a concentrated load P at the midspan. That is, midspan means center. Find the deflection under the load by strain energy method. So we need to draw the diagram first and then continue with the solution. To begin with the diagram, so it is a simply supported beam. So simply supported beam will be drawn in this particular fashion, or else it will be one end hinged, other end roller can also be classified here. Then it has been subjected, the span of the beam is L, that is the distance between both the support will be called as L, and we shall name this particular point as A and B. That is, point A is the support on the left hand side and point B is the support on towards the right hand side. It is subjected to a concentrated load P at the midspan. Midspan means center. It is subjected to a concentrated load P. Midspan means it is center, which indicates the total span is divided into two parts, which is L by 2 and L by 2 on the either side, so that the total distance shall come out to L. And the position where this particular concentrated load is placed, we shall name that particular position as point C. And with reference, we need to find out deflection under the load. That means we need to find out deflection at point C, which indicates we need to find out delta C or else small delta c. So because of this particular loading, as it has been loaded on the top fiber of the beam, this particular beam will deform in the downward direction. This deformation, the downward direction, is called as a sagging deformation, and we need to find out this particular deflection, that is nothing but delta C, which will be a maximum deflection. It has been placed at the center position. So to find out this, we need to adopt strain energy. Now the main contention here is to find out what is the strain energy stored by the whole beam. So strain energy stored by the whole beam, we need to identify first. So we need to check out strain energy stored due to whole beam. So that means whole beam is divided into two parts, which is whole beam, that is AB, is divided into two parts, and those two parts is CA and CB. So if we add up both, so we will be getting the strain energy stored in the whole beam, which indicates we are going to add up the strain energy stored, strain energy in CA plus strain energy in CB, that is on the left hand side and on the right hand side. So this will be nothing but the strain energy stored onto the left hand side from the point, that is the point where the load has been placed, and strain energy placed towards the right hand side, the point where the strain energy is been, that is the load has been placed. So total beam will be divided into two parts, which is CA plus CB. CA plus CB, if we add, it is nothing but the strain energy of the whole beam. That is what we need to find out. Now to find out this, we need to find out first the reaction component. As the load has been placed at the center, directly we can write it as P by 2 and P by 2 because it is symmetrically placed. Or else we need to find out the reaction as summation Fi is equal to 0, which will be Va plus Vb minus P is equal to 0. That is equation of equilibrium. So Va plus Vb is equal to P, equation number 1. Then consider moment with respect to A is equal to 0, which will be Vb into L, which rotates in the anti-clockwise direction, minus plus P into L by 2, that is equal to 0. That is, with reference to A, Vb will rotate in anti-clockwise direction minus Vb into L. That is, distance between A and B is L, so Vb into L. Same thing, with reference to A, P shall rotate in clockwise direction, so positive. Magnitude of the load is P. Perpendicular distance between A and P is L by 2. So P into L by 2. So Vb into L shall come out to P into L by 2. So L gets cancels up. VB is equal to P by 2. So that is the reason why VB reaction will be P by 2. If you substitute back in equation 1, VA will be equals to P minus P by 2, which will be VA will be equals to P minus P by 2, which VA will be equals to P by 2. So for that reason, directly we can write down either if it has been placed at the center, the load will be shared equally. So P by 2 and P by 2 will be the reaction component, or else we need to adopt these particular equations of equilibrium to find out the reaction component. So this is what we have calculated the reaction component. So as stated earlier, strain energy will be considered in the member CA, and strain energy will be considered in the member CB. So if we consider this particular part in the member CA, that is C is been placed here at the location at this midpoint and A on the left hand side. P by 2 is a reaction component at point A. This is the position for the CA. If I find out the moment with respect to position here, with reference to C, load P is acting upward, which indicates it will rotate in clockwise direction. M will be P by 2 into X. Any distance X, if I consider till the position where it reaches, I shall consider, that is, its section will start from A and it will terminate at C. So it will proceed towards the left hand side. So as the section starts from A and proceed towards the center position, and it rotates in clockwise direction, so positive, magnitude of the load is P by 2, and X is nothing but the perpendicular distance. Now what will be the value of X? The value of X will vary from A to C. X will vary from A to C. So when X is at A, X value is 0. When it reaches to C, X value is L by 2. So limits of integration that we are going to consider, it will be 0 to L by 2. The same condition we are going to adopt for the right hand side part of the section. If we consider, that is, the strain energy to the CB position. If we consider a section on towards the right hand side, on the right hand side we have VB here, and the magnitude of VB is P by 2. With reference to C, VB is acting upward. What direction to rotate? Anti-clockwise direction. So M will be equals to minus P by 2 into X, which means the section shall start from B and end at A. So it will move towards the left hand side. Here also the section will start from A and end at point C. Here section shall start from B and end at C. So this particular distance with respect to B, it will be called as X. So minus P by 2 into X. Now what will be the value of X now? Again, X value shall vary from B to C, because X shall start from B and it will end at C. Similarly here, X will start from A and it will end at C. X will start from B and it will terminate at point C. When X is at B, it will be 0, and when X reaches at C, the X value will be L by 2. So limits of integration that we are going to adopt for CA will be 0 to L by 2, and for CB it will be 0 to L by 2. So these are nothing but the limits of integration and its corresponding moment values. Here it is positive for the reason VA will rotate in clockwise direction. On the other hand, B rotates in anti-clockwise direction. For that reason, this particular value is considered as minus P by 2 into X. So total strain energy will be equals to strain energy in CA plus strain energy in CB. Strain energy in CB, which is integration. What is strain energy equation now? Strain energy equation is integration m square dx divided by 2EI. So m is the value that we have already calculated. Similarly here m is already been calculated. 2EI is constant. Dx is nothing but the integration part here. That is, with respect to x we need to integrate. So the limits of integration for CA will be 0 to L by 2, whereas for CB it will be 0 to L by 2. So if we write down here integration m square dx divided by 2EI plus integration m square dx divided by 2EI. This is from C to B and this is from C to A. Now we shall substitute the value for C to A, m value. M value for C to A is P by 2 into X. So this is P by 2 into X dx divided by 2 EI integration kept as it is, plus second term. Here m value is minus P by 2. So minus P by 2 into X dx divided by 2 EI. So same we shall rewrite here, which is total strain energy will be equals to integration P by 2 into X dx divided by 2 EI plus integration, this is whole square, m square dx, that is total strain energy is integration m square dx divided by 2 EI. PA, that is CA, is P by 2 into X, whereas here it is minus P by 2 into X whole square dx divided by 2 EI. For the first term, the limits of integration that we had is 0 to L by 2. For the second term also it is 0 to L by 2. So we shall write the limits of integration as 0 to L by 2 and 0 to L by 2. So both the integration we are going to write it here. Now what that first task is to expand the bracket here. Then after expansion we need to integrate it. To start with, this is 0 to L by 2. Integrate the expansion of this will be P square X square 2 integration will be 4. 2 square will be 4 into 2 EI dx, that is nothing but the first term, plus 0 to L by 2. Here minus squared of will be positive. So this will be P square X square divided by 2 to the 4, 4 to the 8 EI dx. So the only change here is the minus will be converted as positive because it will be squared up. Now if we happen to see both the terms are same, so we can certainly write it as 2 times 0 to L by 2 P square X square divided by 8 EI. 4 to the 8, 4 to the 8. So this is what is the expression that we are going to get, that is total strain energy. Total strain energy means it is a strain energy that will be composed of CA plus CB. That is total strain energy. Here we are supposed to integrate now. This will be 2 into P square by 8. P square by 8 is constant. Here it is dx integration. So that's why P square by 8 EI is taken outside. In the integration term, it is 0 to L by 2 X square dx is the integration term. 2 1s are 2 4s are. So this is P square by 4 EI. Integration 0 to L by 2 X square dx. Now we have to integrate this particular X square term. P square by 4 EI. Integration of X square will be X cube by 3. 0 to L by 2 will be a term here now, which will be P square by 4 EI. In the integration term, once we substitute the value of L by 2, this will be L cube. Then 2 cube will be 2 to the 4, 4 to the 8, 8 3 is 24. So this will be the first term. The second term, if I substitute, directly I can write it as 0 divided by 3. So this will be P square divided by 4 EI and into L cube divided by 24. So this is total strain energy. Total strain energy. So simplifying here, this will be P square L cube divided by 4 into 24 shall come out to 96 EI. So this is what is the value of total strain energy. Solution does not end here. We are supposed to find out the deflection. So this is just a total strain energy. This total strain energy should be equated to the external work done, because to have a balanced proportion, the internal work done should be equal to the external work done. So total work done will be, we are going to equate it to the total strain energy, and this strain energy has been created because a simply supported beam is subjected to a point load at the center. As a resultant, a strain energy is created on the left hand side, and similarly a strain is created on the right hand side. Strain means what? It's a total deformation or a form of deformation that is created on the left hand side and also been observed on towards the right hand side. And the strain that has been observed on towards the left hand side will be called as CA, and its strain that has been observed on towards the right hand side will be called as CB. So which indicates if I add both CA plus CB, it will be total strain energy in the member AB. For that reason itself, we have considered two independent parts, and the total strain energy has been calculated in the member AB. So this is total strain energy. So total strain energy is equated to external work done, that is work done by external load. Work done by external load. So which is P square L cube divided by 96 EI. So what is work done by external load? Half P into delta. So here this delta is the position where I had considered. So that is C to A. When I mention C common here and C common here, that indicates deflection has been calculated at point C. So this deflection will be called as point C, because this total strain energy is computed from A to C and B to C. The C is the common point. For that reason, deflection will be calculated as point C. So reframing this equation, P and P gets cancels up here. P on the left hand side, P on the right hand side gets cancels up. So what will be left out here is, similarly, 2 in the denominator and 96 in the denominator gets cancels up. Once 96 gets cancels up, the left out denominator part is 48. So delta C value will be, see here it is P on the right hand side, P square on the left hand side. So what is left out in the numerator will be PL cube, because one P square has been eliminated because of the term on towards the right hand side. In the denominator, 96 has been halved because of the 2 on in the denominator here. So this is 48 EI. So this is the deflection under the load. So what the statement says is, deflection under the load, that is PL cube divided by 48 EI, is a deflection under the load. So this is how, what the statement says is, we are supposed to find out deflection under the load by strain energy method. What strain energy method says is, integration m square dx divided by 2EI is equal to half P into delta. Half P into delta is external work done, and strain energy stored in the member is integration m square dx divided by 2EI. So this is how we are supposed to find out deflection by strain energy method. Thank you. Have a nice day. Hello, welcome to this session on strain energy problems, that is energy principles and theorems. And here we are going to solve a problem related to the strain energy principle that we have derived in the previous session. In the previous session, we have derived the formula for strain energy due to axial loading and strain energy due to bending, that is nothing but flexure. To have a small recap of what was the formula that we had derived, the strain energy due to bending was integration m square dx divided by 2EI. So this will be the formula that we are going to make use to find out a certain parameter that will be applicable. Now in the same derivation, we had considered the work done by any element. Now here the work done by any element is nothing but an average work done that we are going to consider. So average work done here is half P into delta. This is external work done by any element. That is, external work done is P is applied as an external work done, and delta is nothing but the displacement that is going to be considered. So if we happen to recall this particular derivation part, we had considered a bar, and it will be subjected to various types of loading, and it will be subjected to any form of deformation, that is delta. An average part, if it has been subjected to first force P, the deformation will be nothing but an increment in the length will be delta. As we go on increasing the magnitude of the force, again it will be delta 1, delta 2 and delta 3. So this particular external work done is nothing but a force into displacement. So that is why it is an average work done. It is force into displacement. This is an internal strain energy stored within any element after it has been subjected to any form of a bending effect. Now this will be the equation that will make use, that we are going to make use to find out the deflection in any form of beam, that is specifically for the simpler section or the simpler element. To begin with the solution here it is a given statement of the problem. What it says is to find the deflection at the free end of a cantilever beam and carrying a concentrated load P at the free end. So we need to first represent a cantilever beam. So cantilever beam is a beam wherein one end is fixed, the other end is free. So in that particular case, we shall consider a beam and name that particular beam as A and B. And we shall make one end as fixed, the other end as to be free. The fixed end will be named as A and the free end will be named as B. So this is what is a cantilever beam wherein one end is fixed, the other end is free. And the total length of the beam, we shall consider it as L. That is what is called as the span of the beam as L. So we need to find out the deflection at the free end of the beam. So in this case, the free end of the beam is B. So I need to find out deflection at B, that is called as delta B, or else can also be called as small delta B. And why it is to be calculated delta B is because it has been subjected to a concentrated load P at the free end. So which indicates it has been subjected to a concentrated force P at this particular point B. So once it has been subjected to a concentrated force P, we need to find out what direction this particular beam will deform. Since it has been subjected to the vertical load here, the beam will deform in the downward direction. As it deforms in the downward direction, the elastic curve of this particular beam will move like this. So this particular deformation or the deviation from point B to B dash is called as delta B or small delta B. So this is what is called as deflection that we need to solve. So please do remember, this particular we are going to solve by strain energy concept. This we are going to solve it by strain energy concept, because there are again further few concepts that we will come across is Castiglione's theorem and also with respect to the unit load method. Now what we are solving here is a strain energy concept. In case of strain energy concept, you are going to equate an external work done to the internal strain energy stored in the member. So when we are equating it, we call it as the strain energy method. So in this particular case, first we need to find out the strain energy stored by a beam due to subjected to the concentrated load P. So strain energy stored by cantilever beam, is equal to integration m square dx divided by 2ei. So this is what is the strain energy stored by cantilever beam. Now here in each and every term we need to find out the parameter that has been required now. E and I are constant, so we are not going to find out or any value related to this until unless the value of E and I has been mentioned. If it has been constant or uniform or it has not been mentioned, that means we shall keep this as it is. Now coming on to the term M now. Now M is nothing but the moment that we need to calculate. To find out the moment term, the section shall start from B and it shall proceed towards the left hand side. As it proceeds towards the left hand side, the section shall be considered here YY, and with reference to the B point, this section is considered as X. So moment at any position X shall be considered as P into X, because with reference to this section, P is acting on the right hand side which will rotate in the clockwise direction. So that's the reason why it is expressed in terms of positive load into perpendicular distance, so P into X. So this is what we are going to substitute here. Once we substitute the value here, this will be integration P x the whole square dx divided by 2ei. So when we expand this is strain energy stored by the cantilever beam subjected to the external loading now. So once we substitute this we can expand as P square x square, we can expand as P square x square dx divided by 2ei. Now what should be the integration term? We need to expand now. This will be integrated with respect to dx. So integration of x square will be x cubed by 3. There is no problem with respect to that. Now coming on to the limits of integration, or else we need to express in terms of constant of integration. To express in terms of limits of integration, the section shall start from B and it will terminate at A. when the section starts at B, x value at B will be 0, and when it terminates at A, x value at A will be L. So for that reason, the limits of integration shall be considered as 0 to L. So these are nothing but the limits of integration. We shall consider or take out the constant terms, that is p square divided by 2ei outside. Inside the integration term, it will be 0 to L x square dx. So this is strain energy stored due to the cantilever on the cantilever beam. So this is p square divided by 2ei. Integration of x square will be x cube by 3, 0 to L. Integration of x square will be x cube by 3, 0 to L. So we shall substitute here as p square by 2ei, p square divided by 2ei, L cube divided by 3, first term, minus of 0 divided by 3. That is first term L cube divided by 3 minus of 0 divided by 3. So which will be p square divided by 2ei as it is. And in this term, second term will be 0. That is L cube divided by 3 will come as it is. This is strain energy stored now. The same strain energy will be p square L cube divided by 6ei. This is strain energy stored by the cantilever beam. So I shall write it as strain energy stored by cantilever beam subjected to point load, subjected to load P. So this is what is strain energy stored now. Now this strain energy stored shall be equated to the external work done. So when I equate it to the external work done, so strain energy stored will be equal to external work done. So which will be strain energy stored equation what we had just now is p square L cube divided by 6ei. You write it on the left hand side. P square L cube divided by 6ei, which is equal to half P into delta. And this delta what we are going to calculate it as called as delta B. Or else you can also call it as delta B is equal to capital delta B. If you consider or recall that particular beam, the beam was in this fashion. It was a cantilever beam subjected to load P and the span is L and it deformed in the downward direction. And this particular point was B and the deflection was called as delta B. And we are going to find out the deflection at this point now. Now to solve this part, this will be P on the right hand side, P on the left hand side gets cancels up. And 2 ones are 2 3s are. And as a resultant, P and P gets cancels up. P and P gets cancels up. So this will be delta B is equal to PL cube divided by 3EI. So this is what is the deflection that has been caused due to a cantilever beam subjected to a load P at the free end. So these particular values was the same value that we had calculated even by a moment area method or conjugate beam method. The formula was same and here also the formula is same. That is for cantilever beam subjected to point load P, this particular deflection value was PL cube divided by 3i. If you happen to recall by moment area method, so moment area method the bending moment diagram was drawn like this. That is nothing but PL, which is nothing but M diagram. So same M diagram was converted as M by EI diagram, that is PL by EI. Now to calculate deflection here, deflection was moment of M by EI diagram. Moment of M by EI diagram. So here moment means what? Area into X bar. Which means area is nothing but the area of the triangle here, which is half PL by EI, that is height of the triangle, multiplied by the base of the triangle is L into centroid. Centroid shall be calculated from point B because you are finding out deflection at B. So centroid will be calculated from point B. So that particular centroid will be 2/3 of L. So when I substitute here 2/3 of L, 2 gets cancels up. So that particular value 2 gets cancels up and formula will be PL cube by 3EI. That is also called as delta B. So whether we adopt a moment area method, this is what is the solution that we are going to calculate by moment area method. And earlier what we had calculated was, this is the solution that we had calculated by strain energy method. Strain energy method. So wherein we are calculating strain energy is equal to external work done, that is half P into delta is equal to integration half P into delta is equal to integration m square dx divided by 2ei. This concept is what is called as strain energy method. This is called as strain energy method, wherein this particular method is nothing but moment area method. Whether you calculate by moment area method, you got it as the PLQ by 3i, and whether you calculate by strain energy method, again the deflection value is PLQ by 3i. So this is how we are supposed to find out the solution by strain energy method. The most important thing is the external work done will be equated to the strain energy stored, that is half P into delta will be equals to integration m square dx divided by 2ei. So this is how we are supposed to solve for strain energy method. Thank you. Have a nice day.